In this video, we're going to recap your understanding of collision theory, which is something you should have studied during your GCSEs. So collision theory tells us that reactions can only occur when collisions take place. So they actually have to bang into each other, but they also have to have sufficient energy. So when they bang into each other, they might just bounce off one another if they don't have sufficient energy to react. And we know that sufficient energy has a specific name, and that name is the activation energy. So we're just going to write that definition in, that the activation energy is the minimum energy required to start a reaction by breaking the bonds in the reactants. And we're going to call that EA. Okay, so they have to collide with each other, but they still might not react. So what are the reasons they might not react? We've already just mentioned one of them. So one of them is that they might not have sufficient energy. And then the second one, can you remember from GCSE what the second reason is? So our second reason is that they might not be the right way round. They might be in the wrong orientation. What do we mean by that? Let's take a step back and let's think about a reaction that you've come across in your study of alkenes, and let's see if we can put that reaction of electrophilic addition and see what we mean by the wrong orientation. So here we are, we've got an alkene with HBr. Now on the left, we've got what you should recognise as the reaction that you would have usually drawn, and if we were to imagine picking this up, then the area of high electron density in the double bond is going to be attracted to the delta plus H, and so if they've got sufficient energy, a reaction is going to occur. Oh, you might remember your curly arrows went like this. Okay, it's in the correct orientation. Now if we were to take it this other way around, that's on the right, as the Br came close to the double bond, because the Br is delta minus, so let's just do that. As that Br is delta minus, because it's negative and the area of high electron density of the double bond, as they come close to each other, negative and negative are just going to repel, and off it's just going to bounce off. So it's just going to come in and it's going to bounce away. Now, what might happen, like a little magnet, as it comes in close to the Br, then it might rotate itself round so that it's in the correct orientation, like a little magnet flipping around, and once it's in the correct orientation, then it will be able to react. So when they're in the wrong orientation, or they don't have sufficient energy, they're not going to react upon collision. Okay, so these are reasons why not all collisions lead to a reaction. So what do we understand by the term rate of reaction? So rate of reaction is defined as the change, so the difference in the concentration of a substance. So maybe at the start of the experiment there's 1 mole per decimetre cubed, and 10 seconds later there's a half a mole per decimetre cubed, so we've lost a half of our concentration in 10 seconds. So how much might we lose in 5 seconds? Less. How much might we lose in 20 seconds? Some more. So it's a change of concentration in a given time. So mathematically we're looking at a change in concentration. So again, let's just take this onto another piece of paper and have a think about it. So the units of concentration are moles per decimetre cubed. So we're doing a change in concentration in a given time. So over a certain amount of time. Like we'd say a car drives in miles per hour. We're going in a given time, and the unit of time is seconds. So if we were to bring that all onto one line, because units in A-level are all expressed on one line, mole dm minus 3 seconds minus 1 per second. Units of concentration per second. So there we go, we've got moles per decimetre cubed per second. And let's have a look at how that happens in our reaction. So if you remember from previous videos, concentration is expressed with square brackets. So if we look at the concentration of a reactant in moles per decimetre cubed over time in seconds. So we're measuring the concentration at different time intervals. Now if it's reactants, where will this curve start? Do you have a lot of reactants at the start or no reactants at the start? we're going to start high up, and our reactants are going to fall. So are they going to fall like this, consistently, all the same, or like this, faster at first and slower at the end? So what do we think? So in general, we're going to see this decreasing, where when there is a higher concentration, there's much more likely to be collisions, and therefore the reaction is going faster. There's much bigger change at higher concentrations, and much slower at the end. So key points are, if you were asked at what time the reaction finished, well, you look at when it's gone flat, yeah? Then we are staying the same concentration, that's when our reaction ends. How do we find the rate of reaction? Now, given that the rate is the change in concentration, so the change in the y divided by the change in time, so divided by the change in the x. So what is that when you do the change in the y divided by the change in the x? So at a particular time, so at this point here, I could do something with a ruler, and that would be helping us to find this change in concentration per unit time, this rate. So what we want to do is we want to put a ruler onto the curve at that time, and we want to draw something called a tangent to the curve. So imagine drawing along the line of our ruler like this. Yeah. We've drawn a tangent to the curve at that particular time, and then we can remove our ruler, and we've got a tangent, and we can measure the gradient by doing dy by dx. And the gradient at any time is equal to the rate at that time. Okay, so what factors affect? And you will have studied these factors at GCSE, so we're going to go very quickly through them. If we increase the concentration, we're going to increase the rate. Could you explain why increasing the concentration increases the rate? So when we increase the concentration, we're physically putting more stuff in the same volume, so there's more particles per unit volume. More particles per unit volume, so more collisions per unit time, and it's the successful ones that affect the rate. So more particles per unit volume, more collisions per unit time. And at A-level, those per unit things are quite important, so try to add that to your GCSE answer. So what about pressure? Pause the video and see if you can write something about pressure. So our answer is actually very similar to our concentration one. Pressure is just about gases. When we increase the pressure, we can do that two ways. We can either put more particles in the same box, so that they bang the sides more and increase the pressure that way, or we can squash the box smaller, so we still get more particles per unit volume, so more successful collisions per unit time. So why does increasing the surface area of solids increase the rate? So increasing surface area increases the number of particles exposed, and so there are more successful collisions per unit time. Now for the last two, we need to be a little bit more careful. This is going to be slightly different maybe to the reasons you were giving at GCSE. The top three answers are all about the number of successful collisions per unit time. These bottom two answers, we're going to change colour because we're going to be looking at having the sufficient energy to cause the reaction. So the effect on rate is more to do with having the appropriate energy, it's more to do with activation energy than it is to do with frequency of collisions. And so the exam board will not want to see answers relating to frequency of collisions, like we've got for our top three explanations. They want to see answers relating to activation energy. And there's going to be much more detail on this and how to answer these questions in pages 9 and 10. But for now, we're just going to write a little brief reasoning, changing colour to just draw your attention to it's a slightly different explanation. So here we go. What's our difference? Well, we know that these things increase rate, but why does a higher temperature increase rate? Because many more particles And we've got an inequality written in here, so make sure you understand what this inequality means. Have energy greater than or equal to the activation energy, so many more collisions are successful. So there are some more collisions as well, but that is insignificant in comparison to them having more energy. So we're going to talk about the more energy. And then catalysts increase rate of reaction without being used up. That's what a catalyst is. How it works is by providing an alternate route of lower activation energy, and how it increases rate is because more particles now have energy greater than or equal to the activation energy, so more of the collisions are successful. Really important that you can spot that these two are about energy, whereas the top three are just like GCSE about collisions.